In this lecture, we're going to be talking about thermodynamics. Thermodynamics is a bit of a physics topic, so this is going to be a very brief introduction to some terms you're going to learn in physics, or maybe you remember having learned in physics, and we're going to look at how they apply to chemistry. Thermodynamics is the study of how heat flows through a system. Thermo, as you may be familiar with, is such as thermometer, is having to do with heat. So when any time you see a word with the prefix thermo, you know it has something to do with heat. Dynamic is movement, so thermodynamics, hence the study of heat, how heat is moving. In order to talk about heat, we need to first talk about where does heat come from. Heat comes from energy. Energy in the general sense is the ability to do work. In chemistry, we're going to focus on heat as being the ability to produce heat. When it comes time for us to do quantitative measurements of how much energy there is in a system, we're going to be using joules, and you can use calories, but we're going to be primarily using joules as our way to measure how much heat is. So the units for measuring heat would be joules, just like the units for measuring temperature would be Celsius, Kelvin, or Fahrenheit. This is how joules are measured. In previous lectures, we've talked about the law of conservation of mass, in which we've said that during a chemical reaction, the mass that you're provided with in the reactants is going to be equal to the mass that is produced with the products. And you may have chemicals being changed from, for example, water may melt and become steam, or you may have water and it could break down to be hydrogen gas and oxygen gas, but the mass is conserved. Here we're going to look at something very similar, which is the law of conservation of energy. And the principle is the same. It's basically saying that energy is not created or destroyed. It can just be converted from one form of energy to another, or it can be transferred from one object to another. But energy is never going to disappear or going to come out of nowhere. This is also stated in the first law of thermodynamics. And there are many laws of thermodynamics, but the first one states that basically the energy of the universe is constant. So you could think of this universally as the sun is providing energy, and that energy comes from fusion of different atoms in its core. That energy that's released is then radiated out into space, and where it is going to be hitting the earth, goes into the earth and is absorbed by the concrete, the plants, people. We feel warmth. And so that energy, we can then convert that energy into other sources, solar energy, for example, to use in our homes, or plants convert that energy into chemical energy through photosynthesis. But that energy is constant. We get more of it from the sun, but we can't create energy from nothing. What we can do is convert it from one form to another, but the energy in the universe is constant. Just to provide you with a little more background on energy, energy is basically broken down into two types. There's kinetic energy, which kinetics is the study of movement. So kinetic energy would be energy of objects that are in movement. And in chemistry, we think of that as basically the speed of molecules, but it could be the speed of anything. There's also potential energy. Potential means your possibilities. So this is sort of the amount of energy an object could have when it is put into motion. A good diagram of this is we see that kinetic energy could be shown in this ball that's being pushed down the hill. This other example is a good picture of potential energy, because we know that when the ball starts to roll down the hill, then it's going to have kinetic energy. But right now it has lots of potential to roll down the hill. If the ball was not at the top of a hill, it probably wouldn't have much potential energy, because it's not going to roll by itself anywhere. But at the top of the hill, if it just gives a little push, it'll continue to roll without someone else providing movement for it. In chemistry, when we think of potential energy, we basically think about the energy stored within the bonds of a molecule. We're not going to be so concerned with springs or balls or pendulums like you will when you go to physics, but that's where we're going to look at potential energy. For the rest of this unit, we're going to focus on kinetic energy. Kinetic energy and potential energy can be transferred from one to the other. But again, remembering what we just looked at with the law of conservation of energy, we know that energy needs to remain constant. Let's look at an example of this. In this animation, there's a block of ice right here, and it's on a frictionless slide. So this is not very realistic, because there's nowhere in the world that there is no friction. But we'll imagine that there's no friction acting against the piece of ice here. So this piece of ice right now has a lot of potential energy because once it is allowed to move, it will move on its own due to gravity. Once it's moving, though, then it has kinetic energy. So this bar is going to show us how energy is conserved. So as you see, when the ice is moving, most of the energy is in the form of kinetic energy. When it gets to the top and stops moving and reverses direction, most of the energy then is potential energy. So this is a good demonstration of how the law of conservation of energy is at work. In the real world, there would be a third sort of source of, not really energy, but there would be a third bar here, which is friction. And we would see that this piece of ice would eventually stop moving because friction is going to cause energy to be lost to the surroundings as heat. Another example of kinetic energy and potential energy is if we have two balls that we're holding in the air. Imagine these are two balls that are, they're not bouncy balls, like maybe, or think of it as like a beanbag or something. But one of the balls is going to be allowed to just go to the ground and stay flat. The other one is going to be able to bounce up and down, and we will see that kinetic energy is being transformed to potential and potential back to kinetic energy. You'll see that when the first ball, when it lays on the ground and it sticks there, it's basically going to all turn into heat because all of that energy that was in the ball, that was potential energy, as it was falling, it was potential energy. And once it hits the ground and it's not allowed to move anymore, that energy is going to be heat. And it's basically because the friction with the ground is going to prevent the ball from bouncing up. You can find both of these animations at www.scienceanimations.com. So up here, this graph has, again, confirmed for us that the kinetic energy and the potential energy, they make up the total energy of the system because this is a system that they were showing without friction. And we see that energy, again, is conserved. So let's go back to chemistry. So again, in chemistry, we're concerned with kinetic energy this time, and we're going to be looking at the kinetic energy and how it flows through a system. So when you have the flow of energy from an area where the molecules are moving very fast, meaning they have a lot of kinetic energy, to an area where the molecules are moving very slowly because they have less kinetic energy, we refer to that as heat. This is a little bit different than you're used to thinking of when you think of heat. Usually we think of heat as just a temperature. Heat and temperature are very different. So heat is almost like osmosis or diffusion, where energy is being moved from an area of low concentration to high concentration. So while heat is looking at how that energy moves, temperature is sort of an average measurement of the energy. So if you have a sample and you're looking at the average kinetic energy of every molecule in that sample, we measure that as temperature. So let's look at this animation of how heat is conducted. So what we see here is we have some sort of a substance, and it is next to a flame. So as we can see, the molecules that are closest to the flame, or maybe these are atoms, we're not sure, they are going to be moving faster. We see that as they turn purple and then red and they start gaining energy from the flame, they are moving faster. And they're going to bump into their neighboring molecules more, which then bump into their neighbors and their neighbors and their neighbors and their neighbors. And soon we see that this whole substance is warm. If we look at it again, we see that the molecules are starting off very slow. As they start to change color, we can see that they are moving faster. So we see that heat is being conducted when the energy is moving from an area of where there is more movement to an area of less movement. And the change in color is indicating a change in temperature. And that change in temperature is a measurement of the average kinetic energy of the molecules in that sample. Let's look at a closer view of molecules next to each other and how they are transferring their energy by collision. This is an animation of Newton's cradle. Newton's cradle is an apparatus, or it's kind of a toy, that basically what it is it has a series of balls that are suspended from two lines, so they're sort of cradled in the middle. And what happens is when we pull one up, this ball now has a lot of potential energy. When I let go of it, though, it's going to move, and that potential energy is, as you can kind of see, it's getting pushed to the next ball and the next and the next and the next and the next. So in a perfect world, as we saw in the demonstration earlier where there was no friction, we would see that these balls would keep bouncing back and forth, going from potential to kinetic, and then the transferring kinetic from one ball to the next, to the next, to the next. But in this diagram, they're going to show that they will eventually slow down because there is friction. So although molecules are not really moving back and forth like these balls are, the idea is the same, where as one molecule bounces into the other, it's transferring some of its kinetic energy to that other molecule. And so now we see, because of friction, the balls are starting to slow down. But again, this animation, this is called Newton's cradle. An important consideration to make also when you're looking at how molecules are moving is, where does that energy come from? So one thing we're looking at here is the energy that is in this substance now is coming from the environment. So we have a couple vocab words that you need to know. This is the system. The system is the set of molecules or whatever particles that you are concerned with. The surroundings is whatever else is going on in the environment. So this Bunsen burner would be part of the surroundings. Whatever the pressure of the environment would be part of the surroundings. Maybe this substance that would be kind of strange, but is also in an ice bath. So those are part of the surroundings. When energy is coming from the surroundings into the system, that is what we call an endothermic process. Endo means entering or from within. So when that energy is being added from the surroundings into the system, we call it an endothermic process. When we have the energy is leaving the system, that is referred to as an exothermic process. Energy is exiting the system. An example of an exothermic process is a chemical reaction where you have two chemicals in some sort of a container. When they mix and they react with each other, they are going to give off energy. That energy flows out of the hot pack and into, if you're holding it with your hand, it flows into your hand. And so that transfer of energy from the reaction in the system to the surroundings, which would be your hand, is what we feel is hot. A different set of chemicals, when they mix together, might actually absorb energy from your hand, and that's how they make an instant ice pack. So in an ice pack, you have those two chemicals, and they require energy in order to react. So they remove energy from their surroundings. So they're removing energy from your hand and pulling them into the system. And we feel that as cold. We'll look at energy for reactions a little bit later. This time we're going to focus on the energy that's associated with phase change. If you have a phase change where you are freezing water, even though that doesn't feel warm to us, that is an exothermic process, because water must have, the energy in the water must be removed in order for it to go from the solid phase to the liquid phase. In order to go from the solid to the, solid to the liquid phase, you're going to need to melt the ice. So you're going to need to add energy, and we already know that. You need to add energy to melt ice. But what's happening is the energy from the surroundings are being absorbed into the piece of ice, allowing the molecules of water in the ice to have greater kinetic energy, and so then they are able to move into the liquid phase. Let's look at a quick animation of this. If we were to look at a microscopic view of ice, and here ice is absorbing heat from the surroundings, we would see that the molecules in the ice are held together by hydrogen bonds, which we're going to look at in the next lecture. As heat continues to get applied to the ice sample, you're going to see that the kinetic energy of these molecules goes faster, and they are able to move faster to break their hydrogen bonds. And once they have all broken free, we now see that we are left with a puddle of ice. We'll look closer at this in the next few lectures.